All right, let's do 3.5, derivatives of trigonometric functions. So we're adding a new function to the list of stuff you can differentiate. We're adding 6 new functions to the list of stuff you can differentiate. And as promised, whenever we encounter something new, we'll probably have to go back to the definition of derivative to deal with it initially. And that's what'll happen. Okay, so we had established a couple of limits. In section 2.4, it's shown that the limit as h approaches 0 of sine h over h equals 1. Prove that with the sandwich theorem. And the limit as h approaches 0 of cosine h minus 1 over h equals 0. And we actually showed that using this other result. So these were established with the sandwich theorem. It's really the reason the sandwich theorem was introduced at that stage. We've evaluated bunches and bunches and bunches of limits by factor, cancel, substitute. Not these two. These were not evaluated by factoring anything. Once you know more properties of sine and cosine functions, this will be some things you'll do with series in calculus too. Turns out if you have a different representation for these functions, these limits can also be evaluated by factor, cancel, substitute. But beyond us for now, we've established it with the sandwich theorem. So we're going to use those two limits. And the whole reason we did those two limits was to do the following. Use these to differentiate sines and cosines. Once we can differentiate sines and cosines, we can differentiate all 6 trig functions because we know the other 4 in terms of sines and cosines. Let's recall, just in case this ain't on the tip of your brain, the summation formula for sine, established in pre-calculus somewhere. I think it's probably mentioned in somewhere in chapter 1 also. The sine of a plus b is the sine of a times the cosine of b plus the cosine of a times the sine of b. Okay, summation formula for sine, it's from your past. We're going to use that along with those two limits just mentioned to show that the derivative of the sine function is cosine. Derivative of sine is cosine. Let's establish that. Okay, so back to the definition. We'll represent sine x as y equals sine x. So then the question is dy dx equals what? We'll go to the definition of derivative. The limit as h approaches 0, the function evaluated at x plus h minus the function evaluated at x divided by h, limit of the difference quotient as usual. Do you know what the sine of x plus h is? You do now because we just stated that summation formula. So that gives us sine x cosine h plus cosine x sine h. Applying that summation formula to x plus h, we stated it in terms of a plus b, so make those substitutions. That produces this. Let's see, we got a sine function here and another one over here. So let's factor this sine function out of those two terms. That'll leave us with a cosine of h and just a 1 here. The other term, cosine x sine h, is left over here, just algebraic manipulations. Now the limit of the sum is the sum of the limits, provided the constituent two limits exist. They will, as we'll see. We get the limit of this first term plus the limit of this second term, taking the h and distributing it in the denominator of each of the constituent pieces. And hey, here's that cosine h minus 1 over h thing we were talking about a second ago. And here's that sine h over h thing we were talking about a second ago. We also have these sine x, cosine x things inside these limits, but it's h that changes, not x. So limit as h approaches 0 of sine x times this quantity, we can bring the sine x out front. That's constant with respect to h. No h's in sine x. If it was a limit with respect to x, then we couldn't bring this out. We could bring this out, doesn't have any x's in that case. But we can bring the sine x out, it's a constant with respect to h. We can bring the cosine out of the limit, it's a constant with respect to h. And that leaves us just with these two limits. Leaves us just with these two limits. And we know what these are. We know this limit is 0. That was the observation we made at the beginning of the section. We know this limit is 1. observation we made. Here's the observation right here that we made at the beginning of the section. These are results from section 2.4. The reason we did them was so we could do this, it turns out. And simplify, and indeed we get the derivative of sine x, the derivative of y equals cosine x. Let's differentiate cosine. But first, let's run back to the notes. Guess what we need to differentiate cosine? We'll need a summation formula for cosine as well. Ooh, let's do a super quick little example too. Let's do that while we're here. Pretty humble. Differentiate y equals 3 divided by x plus 5 times sine x, number 2 from this section. A piece of cake, not very involved, not terribly enlightening, but we just started differentiating trig functions. Let's take the 3 divided by x plus 5 sine x. How about we write it as 3x to the negative 1 plus 5 sine x? Then I don't have to use a quotient rule over here. I can just use a power rule for negative integer exponents. Then we get, by differentiating, derivative of x to the negative 1 is negative x to the negative 2. Subtract 1 from the exponent. Derivative of sine is cosine. I'll put those in square brackets because they're derivatives. Not so hung up on that when something is this elementary. You're really mostly using my square brackets when we have products and quotients and other things to come. But what the hell, we'll put those in square brackets because they are derivatives. And simplify a very little bit, and here's what we get for the derivative. So straightforward differentiation for just sines. Of course, we'll put these sine functions in products and quotients here. We'll actually do that in this section. Let's differentiate cosine as well. Like I said, we'll need a summation formula for cosine. Cosine of a plus b is cosine a cosine b minus sine a sine b. See chapter 1 for a mention of that. I don't think there's actually a proof in this book. See a pre-calculus book for a geometric argument of the proof. I've got notes out there on proofs of these. But there's a summation formula for cosine. So let's differentiate cosine. Rumor is derivative of cosine is negative sine. Let's see if we can find where that negative comes from in the derivation. All right, what you're going to do, we're dealing with a brand new function, cosine function. Well, and I'm going to approach it with a definition of derivative. So we'll find that the derivative is the limit as h approaches 0 of the difference quotient as it was before. We got an x plus h here. That's why we need the summation formula. So the cosine of x plus h is cosine x plus, times cosine h minus sine x, sine h, summation formula stated earlier. Okay, we've got our cosine here and here. So let's factor that out, leaving us with a cosine at h minus 1, same kind of thing we did before. Over here, we've got a minus sine x, sine h. So I was going to say, where did the negative sign come from? I think it came from right there. I think it came from that summation formula for cosine. That's what gave us the negative sign that's ultimately going to appear over here. So factor cosine out, move this term over, split it up as a limit of a difference. Limit of the difference is the difference of the limits, provided both of the constituent limits exist. We can bring the cosine x outside of the limit of h. We can bring the sine x outside the limit of h, leaving us with same kind of thing we had before. Leaving us with this. You know this limit is 0. You know this limit is 1. That's what we observed earlier. That comes from the sandwich theorem. And indeed, we're left with 0 minus sine x. We're left with negative sine x. Yeah, and that negative sign, it came out of the summation formula for the cosine function, if you want to keep track of those kinds of things. So derivative of sine is cosine. Derivative of cosine is negative sine. We'll see some patterns when we differentiate all the trig functions, and I'll try to, in passing, mention some little tricks to remember the patterns. Let's do an example. Let's do 4 examples. Let's do an example related to something physical. So this ties in with the previous section on simple harmonic motion. Okay. And here's the story. It's about a mass on a spring. A weight hanging from a spring is stretched down 5 units beyond its rest position and released at time t equals 0 to bob up and down. Its position at any later time t is s equals 5 cosine t. What are its velocity and acceleration at time t? So they've given us position, and they ask for velocity and acceleration. Velocity is the derivative of position. Acceleration is the derivative of velocity, or if you like, acceleration is the second derivative of position. Okay, this one has one little oddball characteristic. Here's the s-axis, and notice it points down, so that's a little weird. It's a little odd way to apply this, but that's how they've set it up. And their story is that this mass hangs on the spring, and if you leave it alone, it'll hang down here at an S value of 0. Their story is they've stretched it down 5 units, so they've grabbed a hold of it, pulled it down 5 units, stretching the spring, and then they release it, and then it just bobs up and down, as they say. Going up to a position of s equals -5 and down to a position of s equals 5. So that's the physics behind it, and that's the oddness of the way they've done this in terms of having negative up and positive down. That's pretty weird. I'll be careful when I describe what happens to describe things in terms of s increasing and decreasing instead of a description in terms of up and down, because the up and down stuff is kind of backwards on this one. But that's what they've given us. Okay, the position is s equals 5 cosine t. So the velocity is the derivative of that. Derivative of cosine is negative sine, so the velocity is -5 sine t. And acceleration is the derivative of velocity. Differentiate that sine function, it becomes a cosine function. And the ultimate acceleration is -5 cosine t. So there's velocity, there's acceleration, there's the answer to what they asked. So quite easy, but let's go through and look at it in a little more detail. But that does answer the question they asked. Here's a graph where position is graphed in blue and velocity is graphed in red along the same time units. Time's actually measured in terms of, looks like it's measured in terms of angles. It's because we're dealing with trig functions. And look what happens here. Initially, this is position. The mass has a position of s equals 5. That position decreases down to 0, where it's at its rest position, s equals 0. Then it decreases further to s equals -5. Now, that's what we get out of the graph, and then it turns around and goes back, and it oscillates back and forth. But let me go back to the original picture, going back to the previous slide. Here's s equals 5, and we said it as time increases, then that s value decreased to 0 and then decreased to -5. So actually, the s values are decreasing, yet the weight is moving up. That's because they've got the axis pointing down. But we see s go from -5 to 0 and then 5, then the spring's really compressed, so it pushes back, and the weight starts to move in the other direction and oscillates back and forth. Okay, so that compression of the spring is what we get from time 0 to time pi. Here, the spring is compressed, and now it starts to push the weight in the other direction. Then the weight gets really stretched, the spring gets really stretched, and starts to pull the weight back. So that's why we get that kind of oscillation. In red, we've got graphed the velocity function. So you might notice that the weight has between 0 and pi, between here and here in time values, the s values decrease from 5 down to -5. So we've got a decreasing function. Its derivative should be negative, and its derivative in red here is negative between 0 and pi. At this position, at time pi, the weight starts to have increasing s values, and from pi to 2 pi, pi to 2 pi, this function increases, and its derivative is positive. Increasing functions, positive derivatives, decreasing functions, negative derivatives. You should be used to that by treating derivatives as rates of change. And we can make some little observations about, hey, when the red one is 0, the blue one should have a horizontal tangent line. That happens at 0, yeah, it's a little horizontal tangent line there. It happens at pi, yeah, little horizontal tangent line to the blue one here. Happens at 2 pi, blue one, little horizontal tangent line. And of course, it's periodic and repeats its behavior every 2 pi units of time. Let's see, trying to describe this somewhat in terms of more physical things as well. At 0 pi, 2 pi, the velocity is 0. What's happening there physically is the weight has either reached its maximum S value, it's gone down, it stopped going down, it's going to start going back upward. Or it's gone upward, stopped because of the pressure, the force from the spring, and it's going to start moving back down. So we actually see the spring go down, well, have decreasing S value, I should say. It's actually going up over this interval. That bugs me, but that's what they've given us. But we have decreasing S values. Here we're reaching a case where the spring is really compressed and the weight stops moving. Yeah, its velocity is 0, its speed 0 as well. And turns around and starts to move in the other direction, let's say. Yeah, the velocity has gone from negative to positive, it looks like. Maximum speed, you should be able to visualize, will occur when the weight's in the center, when S equals 0. Is that right? Speed would be the absolute value of velocity. We've got the mass at S equals 0 when the blue one has an intercept. So here, yeah, this is maximum distance from the axis. If we take the absolute value, we get a value of, I guess it's 5. They didn't give us units, 5 somethings per second, say. But yeah, velocity is a maximum. Magnitude here, velocity itself is a minimum, but its magnitude, its absolute value, its speed is a maximum at these extremes. And all those maxima are the same. So there's a physical interpretation, of course, as well. The acceleration we found to be -5 cosine t. That's exactly the negative of what we started with. We started with position as 5 cosine t, and the acceleration is a negative of that, telling us the acceleration is always proportional to the negative of its displacement. The negative of the displacement, we denoted by S, would be -5 cosine t. Yeah, these are proportional, and that constant proportionality is 1 in this case. But when you have such a situation where acceleration is proportional to the negative of displacement, that's something called Hooke's law, and you've possibly heard of Hooke's law in connection with springs before. It's sometimes maybe even called the spring law. But there's something physical that relates derivatives in sines and cosines. We talk in sines and cosines and derivatives, and we're talking velocities and accelerations and positions. We got to mention simple harmonic motion. We got to mention this spring stuff. Let's take some more derivatives. Okay, you know how to differentiate sine and cosine. That means you know how to differentiate all trig functions, because you can write all trig functions in terms of sines and cosines in a product or quotient format, and you know how to differentiate products and quotients. Question here is, for p equals 1 plus cosecant q times cosine q, find the derivative, find dp dq. Use them with square bracket notations, part of the instructions. All right, what you gonna do? All you know how to do is differentiate sines and cosines. I'm gonna turn this into sines and cosines. This part I'm happy with. Cosecant, we'll have to turn that into sines and cosines. If memory serves, this will get in your head because we're going to use it so much. Cosecant is 1 over sine. Should sound familiar. So let's take the cosecant and replace it with a 1 over sine, so that differentiating the original function is equivalent to differentiating the function 1 plus 1 over sine q quantity times cosine q. So replace the cosecant with a 1 over sine. All right. That gives us a product, and here's a quotient. I see a quotient inside a product rule. Okay, so product rule says derivative of the first, here's the derivative of the first, times the second, the cosine, plus the first, this thing, times the derivative of the cosine. And I've done the differentiation in this step. Oh, when we differentiate this first one, derivative of 1 is 0, and this is treated as a quotient. So I see square brackets, parentheses, parentheses, square brackets. I see a product rule. Within that, I see square brackets, round brackets, minus round brackets, square brackets over round brackets squared. I see a quotient rule. So that's a quotient inside of a product. All right, so differentiating, let's see, we need the derivative of the first and that product rule stuff. Derivative of 1 is 0. Here we need a quotient rule. Numerator is 1, derivative of 1 is 0, denominator is sine q, minus numerator 1 times the derivative of sine. Derivative of sine is cosine q, over the denominator squared. Let's not simplify yet. Maybe we'll clean this up a little bit. But we'll leave it like this for now so I can see where everything came from, and it makes it easy to double check. Where are we? We're in the middle of a product rule, and we've done derivative of the first, which we had to apply a quotient rule to. Here's a second, plus the first, derivative of cosine. Derivative of cosine is negative sine, q in this case, and all else being equal, there's a derivative. If I don't simplify anything, I got the derivative really in one step. Let's clean it up a little bit. I'm not that big on cleaning up derivatives unless I'm going to do something else with them. In the next chapter, we're going to use the derivatives to do lots of stuff. So we'll clean up things more then and take more of an interest in simplifying. But this is certainly an acceptable, in my opinion, an acceptable answer to the question, find dp dq, because there it is. But let's clean it up a little bit. I want to get a little bit more mileage out of this. Let's see, let's lose the 0 times, and let's use that 1. So that'll leave us with, so it loses 0 as well. Maybe not. That'll leave us anyhow with a minus cosine q over sine q squared, cosine q over sine q squared. Here's the cosine. Distribute over here, you'll get a negative sine q and a negative sine q over sine q. We'll do some cancellation on the next slide. So here's where we left off. We'll cancel these. Assuming sine q isn't 0, that's still implied by some information that's over here, so we still have that information. So we'll cancel there to get a minus 1. Let's take this cosine q over sine squared q and write it as 1 over sine q times cosine over sine q. I still got sine squared in the denominator, right? Right. Okay, I got my reasons for doing that. You can't argue with the validity of it. And 1 over sine, I believe that's a cosecant. That's kind of how this question started. 1 over sine is cosecant, and cosine over sine is cotangent. Maybe review some of that trig stuff. It's in section 1.3, I think, has review of trig. But these are trig identities that produces this, and then I've got the other stuff over here. And let's put a little asterisk by that and observe. You see this stuff in square brackets? That ultimately, it's the derivative of this. Well, the 1 doesn't contribute anything. Its derivative is 0. The derivative of cosecant q is negative cosecant q, cotangent q. That's the reason I wanted to keep that stuff isolated. So from this start equation, we see that the derivative of cosecant is negative cosecant cotangent. We're going to find the derivatives of all 6 trig functions. We just accidentally stumbled across the derivative of cosecant. And if you want to clean this up a little bit, then I can write the derivative in this form. Okay, so there's combinations of products and quotients and derivatives of sines and cosines. The next question or questions have us go through and find derivatives of, see what's left, tangent, cotangent, and secant are the other 3 left. We've done sines and cosines by definition. We just did cosecant using the quotient rule. Okay, differentiate tangent. Well, tangent of x is sine x over cosine x. trig identity from your past, your pre-calculus past. It's quotient, use the quotient rule. We'll have derivative of the numerator. Derivative of sine is cosine. And I'm not doing the differentiation at this step, as you can tell by the fact that there's no ddx stuff like I had done in the past when we first encountered product and quotient rules. So I'm skipping one layer of writing and going straight for the computations. You know this is a derivative because it's in square brackets. Derivative of sine is cosine, derivative of the numerator, times the denominator, minus the numerator, sine, times the derivative of cosine, which is negative sine, divided by that denominator squared. There's the derivative of tangent. I definitely want to clean this up. This is what cosine squared, sine squared plus sine squared, cosine squared plus sine squared. We got a cosine squared in the denominator. Hey, cosine squared plus sine squared equals 1. Pythagoras told me so. Your hopefully best known trig identity. Cosine squared plus sine squared equals 1. So we get 1 over cosine squared. 1 over cosine is secant, so we've actually got secant squared. 1 over cosine equals secant, recall from trig identities. And the derivative of tangent is secant squared. Piece of cake, I told you so. Once we can do sines and cosines, we can do all 6 trig functions. Let's do the other 2. So secant and cotangent are left. So let's do those. Question 62, part A and part C. Part B is probably cosecant, but we've already done that one. Okay, so we'll differentiate secant. That is, differentiate 1 over cosine, as we just observed. Secant is 1 over cosine. That's a quotient. We got a quotient rule. Derivative of the numerator times the denominator. Derivative of 1 is 0, denominator, minus numerator 1 times the derivative of cosine, that's negative sine, derivative of the denominator, over the denominator squared. Clean it up. Let's see, 0, that's gone, 2 negatives. We've got sine over cosine squared. Let's split that up as 1 over cosine times sine over cosine. Multiply, it's still sine over cosine squared. I won't do that because I want to write it as a product of 2 other trig functions, these 2. 1 over cosine is secant and sine over cosine is tangent. Recall these identities. So the derivative of secant is secant tangent. Putting the derivatives in this form because I'm looking for a pattern that's easy to remember because we're going to do bunches and bunches and bunches of differentiation with trig functions. How are you going to do cotangent? Probably awfully similar to the way we differentiated tangent. I'll write it as a quotient, use the quotient rule. Well, let's do that. Okay, cotangent is cosine over sine. Recall, cotangent, cosine over sine, quotient. Quotient rule, derivative of the numerator, derivative of cosine is negative sine. Denominator is sine. Minus numerator, cosine. Derivative of denominator, derivative of sine is cosine, divided by denominator squared. So there you go. Let me sing my praises again. Jesus, square bracket stuff is awfully useful because there's sines and cosines all over the place. Some of them are derivatives and some of them aren't. Well, I can tell easily which ones are derivatives. It's these 2 because they're in square brackets. It's just bookkeeping, but it lets me keep up with what's derivatives and what isn't. Let's see, this is a negative sine squared, minus cosine squared. If you'll factor the negative 1 out, there's no parentheses there. We'll get negative sine squared plus cosine squared. That is negative 1 over sine squared. 1 over sine is cosecant, and this reduces to negative cosecant squared. So there's a derivative of all 6 trig functions derived from stuff we know. Sine and cosine derive from the definition of derivative. These other ones derive from sines and cosines derivatives and quotient rules. Back to the notes. So I have a synopsis of that. Here's what we've got in summary for the derivative of the 6 trig functions. Okay, and I split it up in a way to look for patterns. Sine, cosine, tangent. Cotangent, secant, cosecant. And the little pattern here is as follows. This is what we get computed. We've demonstrated all of this. Some of them start with a negative sign and some of them don't. Which ones start with a negative sign? Cosine, cotangent, and cosecant. So the cofunctions have derivatives that start with a negative sign. And the non-cofunctions, sine, tangent, and secant, they don't start with a negative sign. I'm not saying that thing is negative. I don't know. And it starts with a negative sign. Yeah, sine x itself could be negative. So I'm not making that claim. I'm just looking for format and a pattern on how these things behave. There's a second pattern. If you'll take any function, any one of these lines in this table, any one of the rows in this table, and you'll replace every function with its cofunction, you'll get another line. If you'll keep in mind that thing about cofunctions have negative derivatives. For example, let's do this one. Let's do secant x has as its derivative secant x tangent x. If you replace each of those functions with their cofunctions, this would read cosecant x, cotangent x. Well, that's the same thing you got down here, except we didn't get the negative sign. We'd have to manually put that in. So anyhow, I'm just looking for patterns that make this easier to remember. If you can remember the derivative of, say, sine, tangent, and secant, you can figure out the other three. And we will use derivative of sine, tangent, and secant rather extensively. We'll use derivative of cosine rather extensively. We'll use derivatives of cotangent and cosecant somewhat less. It turns out, I mean, that's just the nature of Calculus 1, it turns out. We'll do these, but we'll do less of the cotangents and cosecants. But anyhow, there's what you need to know about derivatives of the 6 trig functions. Let's do a couple more examples. Here, they ask, does the graph y equals 2x plus sine x have any horizontal tangent lines in the interval x between 0 and 2 pi? Horizontal tangent lines. How do you find the slope of a tangent line? Taking derivatives. What's the slope of a horizontal line? 0. So this question is effectively, is the derivative of that function 0 in the interval from 0 to 2 pi? Okay, well, let's find the derivative. First, the derivative of 2x is 2, derivative of sine is cosine. So y prime is 2 plus cosine x. There's the derivative. A tangent line of the graph of this function has slope y prime as a function of x. So here's slopes of tangent lines. Horizontal lines have slope 0. So we're looking for values of x such that the derivative 2 plus cosine x equals x. So we're really just solving this equation for x. So that's translating the words into the math. This is the same as cosine x equals -2. Well, remember, cosine x oscillates between -1 and 1 for real numbers. If you let me use complex numbers, that's a different story. But for real numbers, cosine ranges from -1 to 1. So there aren't any real x values for which cosine x equals -2. Ask your calculator for the cosine inverse of -2. It'll either present some sort of weird stuff related to complex numbers, or it'll generate an error. So no real values that satisfy this. So no, there's no place where the graph of this function has a horizontal tangent line in the interval 0 to 2 pi. Yeah, well, anywhere. This doesn't happen anywhere. There's no x's that do that, let alone any x's in this interval. That simply never happens, regardless of the constraints on real variable x. So nope, does not have horizontal tangent lines there or anywhere else, by the way. And a final example, evaluate this limit. Okay, now this one's a little tricky. With the stuff we know, can you factor? You can't factor anything related to that tangent function, not with what we know now. I can write in terms of sines and cosines, see what happens from there. Yeah, I got no particular ideas based on what we know. This is a trick, and that's the reason I'm working it for you. So this one's a bit tricky. If I were handed this out of context, I'd probably change that tangent into sines over cosines and see if I could do something that I recognize. And I probably wouldn't have very good luck because I don't know about limits as theta approaches pi force of sine and cosines. So, but here's the trick. Recall the alternative definition for derivative. F prime of x is the limit as z approaches x of f of z minus f of x over z minus x. It was in exercise 3.2.24. We referred to it a handful of times. Well, if you'll set z equals to theta and x equals to pi force and use the function tangent x, then we get tangent of theta minus tangent of pi force, which is 1. So we'd get a tangent of theta minus 1. So far, so good. In the denominator, we'd have theta for z and pi force for x. We'd have theta minus pi force. Well, that's exactly this. So that's the trick. So if we cleverly choose, bad test question because it's more of a trick than anything insightful. If we make these choices for z, x, and the function, then we see that we can rewrite the limit they've given us as this alternative form of the definition of derivative. All right. Well, if f of x equals tangent, then what is the derivative? Derivative of tangent, that was secant squared. Get these in your head because you're going to use them a lot. If you'll do the homework, you won't be able to avoid getting these in your head because you're going to use them so much. But yeah, the derivative of tangent secant squared. Okay, so we've got secant squared x, and what was x in our choice? Pi force. So this limit must equal secant squared of pi over 4. It's the derivative evaluated at x. When we've made these substitutions, the derivative is secant squared of x, and we've chosen x to be pi force to create a limit based on this that is of the form of the limit that we started with. So we must have a secant squared pi force. You remember your special triangles. Secant's 1 over cosine. Maybe I could write it as 1 over cosine squared pi over 4. And cosine pi over 4 is the square root of 2 over 2. Oh my goodness, I got an error here. This should be squared and the ultimate answer is 2. Forgive me. This should be square root of 2 over 2. I left the square off from that cosine. Cosine pi force is square root of 2 over 2. That quantity is squared. That produces 1 over, what does it produce? 1 over 2 over 4, 1 over 1/2, which reduces to 2. Excuse me, I'll correct the notes. This should read 2, not the square root of 2. I left the squaring off. So this should be squared and the answer is 2. But little trick, I'll just go ahead and leave this error in the video, but I'll get it fixed in the notes. This is our last one from this section. It's a trick, and you have to match this up with the alternative form of the derivative. From there, fix my squaring error, and it's smooth sailing. Again, bad test question because it's more of a trick than anything, but this will get you through the homework questions in the book of this sort. And that takes care of this section. All right, so that finishes derivatives of trig functions. What we've got left to do is derivatives of log functions will pop up at some point in the near future, and the chain rule. We still need to do the chain rule. But when we get done with chapter 3, maybe done the 2 or 3 more sections of chapter 3, you're going to know everything you need to know about differentiation. You'll be as good at differentiating as anybody is once we do the chain rule and a couple more functions. So on to that next. Have a nice day.